Hey guys, so I have a new piece of test equipment to show you. I've actually shown this previously, but only took a cursory glance at it and haven't gotten into any detail about what this thing is actually capable of. So I decided to put out a small, short-ish YouTube video discussing a few of its capabilities. I'm not going to try and take it apart. I'm sorry, but it's underneath a stack of quite heavy equipment, and honestly, I can't be bothered. But I will try and do a couple of experiments and show you exactly what this thing is capable of. So a bit of context, this is a model 760 fast Fourier transform spectrum analyzer. It's basically a spectrum analyzer but for audio frequencies, basically, and it doesn't work in the way a conventional spectrum analyzer works, by mixing the RF with a local oscillator and getting an intermediate frequency and filtering that and blah 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 blah. I told you I don't know much about RF. This thing actually digitizes the input, which is on this side here. It's got a single-ended or fully differential input depending on how you configure it in the user interface. It digitizes it, and it does some DSP processing and basically gives you a spectrum of the input. And you'll see that it does that due to the various span settings and center frequency settings. So they're not, you can't set them independently of everything as you would be able to in a conventional spectrum analyzer. So for example, if I wanted a span from 1 gigahertz to 1.1 gigahertz and a resolution bandwidth of 500 kilohertz, I could program that into any spectrum analyzer, but this won't, for example, let me choose anything other than for example, sort of, you can see that there are multiples of something, so 12 and a half, 25 kilohertz, etc. So the full span is from several millihertz to 102 kilohertz, actually, so 1024 kilohertz. And it can go as low as I think a couple of millihertz resolution. So when it comes to frequency resolution in the low frequency domain, this thing is pretty much unbeatable. Now, Stanford Research still manufacture this one, but it's called the 770 now. And the only difference is that the 770 has a built-in low distortion signal generator. So, yeah, it's a significant advantage. Oh, and it doesn't have a floppy disk drive, it has a USB, but it looks identical, it's got the same display, etc, etc. And you can see sometimes it's calibrating its own offsets internally according to the temperature rise of the instrument, etc. So what can you do with this thing? Well, for example, you could mount something like this to a piece of structural steel. So this is a accelerometer that Dennis gave me. It's among the gig tuned oscillator and the rest of the things that I showed you last time. You could mount something like this to a construction steel beam or something like that, hook this up to the analyzer and see if the beam or the structure in itself indeed has any resonant frequencies by smacking it, and then taking a sweep of this thing and seeing if there's any resonant frequencies. in a specific interest band or something like that, or you could mount that on a propeller, or you can use it as a seismograph or stuff like that. So material dynamics is one application for this thing. You can also use it as a quality standard for audio amplifiers. So basically you could have a very well known distortion signal generator feeding into output into a power amplifier, and then you could measure the output into something like a reactive load and see whether the amplifier is introducing anything like intermodulation, distortion, harmonics, and stuff like that. So actually the intermodulation distortion might come from the back, but I'll leave that kind of audio foolery worms away. It can do quite a lot of measurements. So it can do power spectral distribution, it can do octave analysis, you can configure the input as a single-ended or differential, floating or ground referenced, AC or DC coupled. You can change the input range. You can have an external trigger. You can analyze harmonics, sidebands, all sorts of things that I have no idea what they are actually. And yeah, it's very, very, very interesting. And you can see that I was touching it and it's already picking up something coupling through the BNC connector. If I put a 50 ohm terminator, if I can manage to find one, it's not going to be easy. The noise floor should drop a bit, but we'll get to that in a second. Let's see if I can show you the distortion level that the Siglent SDG1032X is capable of. So let me configure that thing and we'll be right back. Right, so when I said PSD, it's not power spectral distribution, it's density. Apologies for that. It's a volts per root hertz figure, basically. So I have the signal generator set to 50 kilohertz and 200 millivolts peak to peak, and I'm gonna hit auto range and auto scale, and we can see that if I hit the marker and go and find the peak, and we have 50 kilohertz spot on, and a peak of 71.98 millivolts RMS, which, considering that we have a 200 millivolts peak to peak waveform, yeah, we're getting pretty much exactly what we should. 0.707 something, so it's pretty close. And now if I go to harmonic and turn harmonics on and add a parameter, and let's say harmonic order 2, we should, the frequency is going to be over. So let's move this down to 10 kilohertz. And first of all, we can already see that without any harmonics applied from the signal generator, the output of the signal generator itself isn't very clean. So let's do a THD measurement. So if we do, I think it's analysis, harmonic, and let's go to number of harmonics. Let's go to 4. And if we go to the marker for this one, so that one's pretty noisy. So analyze harmonic. Let's go down to 3 harmonics, actually 2. So we can see that there's a THD, wait, because fundamental, sorry, 10 kilohertz. So the fundamental is 10 kilohertz, and it's looking also at the first and second harmonic, which are basically 20 and 30 kilohertz. And we're getting a THD figure of 0.125 something percent, which is pretty good. Like, it's not great, but it's pretty good, considering the fact that this peak is 71 millivolts RMS, and this one is about 1,000 times smaller. It's pretty good. Now, you might see that this thing is very, very sensitive. Well, it's both very, very sensitive and very, very low noise. So the noise floor at the moment as it stands is in the single-digit microvolts RMS noise, and we're not scanning particularly slowly, so we're not giving it a lot of time to sweep across and do its processing, so it can go even lower. And I will show you that a bit later. But let's go and add an harmonic, and let's go to the second order harmonic and go to harmonic amplitude. Let's see, and let's make it very small. And despite the fact that I made it very small, it's 10 millivolts peak to peak. The harmonic analysis, if we put the fundamental back to 10 kilohertz, we can see that we increased the THD of the signal by approximately 5%. So it was 0.1%, and now it's 5%. So, and I just added 10 millivolts peak to peak in 200 millivolts peak to peak, which makes perfect sense. So, yeah, let's look at the frequency content of a square wave, because that's very, very interesting to see. Let's look at a ramp first, actually. So you can see that a triangle wave basically has all the even harmonics. So let's see, actually, if I'm talking out of my ass right now. So this is 30. Sorry, it has all the odd harmonics and none of the evens. So like 3, 5, 7, etc. These harmonics here were previously present, so these are part of the clean sinusoidal signal that we are feeding it. And now if we look at a square signal, square wave, I think it's too much signal. Let's turn it down a bit and auto range and auto scale. Surprisingly, it's still showing that it's only got all the odd harmonics. Square wave, it actually, there's a difference. I apologize for that. You can see that the square wave actually has basically the amplitude of the even harmonics is basically the same, whereas for the triangle, the amplitude of the even harmonics is negligible. So this, as we've said previously, I apologize, was already present in the fundamental and the sine wave, and in a square wave signal, they're all there. If we go lower in frequency, so 1 kilohertz, for example, by the way, I apologize, sorry, just smacked you around. Let's go to harmonics and let's go back to 10 kilohertz and let's see the THD. So the THD is a third now, which is, oh, and it's basically taking into consideration only the first two harmonics, but if we fill the thing up with harmonics, it's going to be terrible. should be about 50%, I think. Let's wait for it to calibrate. Yeah, so it's about 42% over the bandwidth that we have available. So give or take half. Let's go back to giving it a smaller, lower input frequency. And let's look at more frequency content. So for the moment, we're looking at 2 kilohertz, the fundamental frequency. And let's look at number of harmonics, let's say 20. Might be too many. But, oh, it's nowhere near enough. So now we're getting closer to the theoretical 50% THD content of a square wave. If we go to a triangle again, we'll see that it's only 12%. So a square wave is much more harmonized than a triangle wave. Right, let's go back to a sine wave. And you can see that the THD is now still pretty low at around 0.1%, which is pretty good. We're looking at a very, very large frequency span, so this is far beyond the human hearing. What we can do is see how low can we go. So right now I'm at 2 millivolts peak to peak, which is still comfortably in the range of the instrument. So the peak is still about 3 divisions above the noise floor, and those 3 divisions are basically, I think, 30 decibels. Oh, 60 decibels, 20 decibels per division. So there's a lot of margin for noise floor in this piece of test gear. It's very, very quiet. Let's look at something more impressive. So let's go to 10 hertz and let's set the span. So let me set the span frequency. Span 100 hertz should be good. Let's put it lower, 24 hertz, and the line width is 61 millihertz. The acquisition time is 16 seconds. That's the only disadvantage of this thing. Really, it's kind of slow. But if we start at 0 hertz, 0 kilohertz actually, so DC basically, or very, very close to DC, we shall soon see that 10 hertz frequency peak out of the noise. And let's turn off the harmonic analysis because we're not using it anymore. So if I go to the marker and go to this thing, we're gonna see the 10.0098 hertz. It's pretty good, right? And it's 700 microvolts RMS. Now, how can we make this even smaller? Well, I have an idea, but it'll take just a second. So what I've done is I've connected this set of probes in the worst way possible. So we have 2 × 10 probes connected far from being coaxial at all. And you can still see the peak is right there. Let's hit auto scale again and wait for it to stabilize for a bit. And you can see that now it's 37 microvolts RMS. But we can go even lower than that, because now, for example, we're at 10 decibel per division, and we still have 1, 2, 3, 4, 5-ish divisions till we get to the noise floor. Actually 4, because I think that's the true noise floor of the instrument, and that was an artifact that we were seeing previously. I'm not still 100% competent with this piece of equipment. It's much smarter than I am. But the question is, can we go even lower than that? And let's see if we can go even lower than that, because I'm pretty sure we can. And it has something to do with multimeters again. Wait just 1 second. Let's see where it settles. So it's again 36 microvolts RMS, and the noise floor is at 7780 nanovolts RMS. So there's still a considerable margin for dynamic range in this equipment. Wait a second, let me set it up and I'll be right back. So I have one of these 101 dividers, and I'll hook the input to the input, the output to the center of the voltage divider, and I'll connect both grounds to the end of the voltage divider if I can. I'll also try to show you at the same time. And ignore what's happening with the analyzer for the moment, because I'm feeding it like massive amounts of noise, and it's not charting anything out. And we'll just give it a couple of seconds and wait for it to get back from its existential dread. And acquisition time should still be around, like now, around 30 seconds, something like that. And we can see some harmonics. I'm actually pretty sure that this one, because I recognize those 8 hertz or something, whatever they are, I'm pretty sure that it's coming from the signal generator. But we're looking at 500 nanovolts RMS of signal, and we can still very clearly make it out. Okay, let's set the span to lower than that, and let's let it average out and relax for a bit. I think these artifacts that we're seeing are basically the filters inside running and working, and we also can turn on 8 averages. So it's gonna take a few minutes. I'm actually gonna pause the video and let it average for a while, and it's saying overload. Oh, it's doing something. I think it's too much for it. I'll bring you back when it's settled down. Right, so I've added 17 averages, and I can't stress it enough. It's like half a microvolt RMS of signal, and it's still picking it up comfortably. This line here is 6 hertz, and I'm not sure where it's coming from. It's almost 7 hertz. I think it's something inside the signal generator itself. But let's do the test of all tests. Let's go to 1 hertz. And this is where everything we knew literally goes out the window, because 1 hertz is basically DC. And let's see if the input is DC coupled. Okay, we were actually doing it a very, very large disservice by having the input AC coupled, because even at what do you call it, at 10 hertz, I think the capacitor inside is gonna ignore everything above 20, 30 hertz or something like that. So you can tell just how sensitive this thing is. Let's wait for it to wake up for a bit and do some math. It's much better at math than I am. And we're looking for 1 hertz. So And you can see that the input is floating, and I floated the input so as to prevent ground loops from appearing. So let's look for that elusive 1 Hertz. It should be around here somewhere. I'm gonna move the marker to where 1 Hertz should be. It should be around here. There it is. It's in the basically the 1/f noise, but enough averaging and we get rid of that as well. So we're looking at half a microvolt RMS of signal, and we can comfortably see it there. And if we auto range and auto scale, it's way to do its thing again. You can see this is an instrument for people who have loads of spare time. Or actually, if you think about it, if you're configuring a measurement at work and the measurement configuration takes 20 or 30 minutes, well, or an hour or so, and that's good for you. You just let it run, go have a break, eat a sandwich, talk to your coworker, and you're still technically working. Right, so let's hit auto scale, and yeah, we can still comfortably see 1 Hertz through a 100, basically, I think it's basically 1,000-ish to 1 division. I'm not entirely sure how the probes behave, the times 10 attenuation in the probe behaves when it's feeding another times 10 attenuated probe. So that's about it. I don't have anything else that I could show very interesting, but you can see this is on a completely different level, so I'm pretty sure that for measuring stuff this is pretty cool. Oh, and we can look at one more thing. Let's see, measure and look at power spectral density for that thing, and we can see that the noise for that thing is 2 microvolts RMS per square root hertz, and that's about it. And we can have, oh, by the way, you can have frequency, logarithmic, scale, linear amplitude, logarithmic amplitude, special, all sorts of stuff like that. And it also has a calculator, and you can use to do all sorts of calculations. So you can, I think you can define an area, so 0.1 Hertz to 10 Hertz, and have it do the peak-to-peak noise for the entire 0.1 Hertz to 10 Hertz. So I was trying to keep the video short, but it still turned out around half an hour long. I hope you're gonna like it. Let me know if you have any more interesting experiments you'd want to see done on this thing. I actually got it to measure the noise for my multi-slope front end. You should be seeing a bit of that pretty soon, depending on how my parts arrive, and if I decide to do any more changes. Damn, those resistors were expensive. Oh, and one more thing, I got the first paycheck from YouTube. It was a glorious $70. Most of it from live stream donations, not from actual views, but I keep doing these things for you guys because I get very nice letters from people, and I love interacting with you guys and hearing from everybody around, and it's the thing that I like to do the most. So yeah, electronics is truly something else, isn't it? Anyway, that's all I got for you today. I think I'll try and do another couple of videos so to make up for the lost time, and since Monday I'm starting the second semester of the master, so I'm not promising that I'll do many videos soon. Oh, one more thing. Somebody asked what can this thing do and FFT function on an oscilloscope can't? Well, this is 16 bits, much lower noise, and good luck trying to get any oscilloscope to do an FFT under, I don't know, a couple hundred kilohertz. No chance. And more than that, there are RF spectrum analyzers that start at 20 hertz, but I don't know of any RF spectrum analyzer that starts at this close to DC, and they won't be able to do the math for that low frequency range. You can see, I think these are thermal effects. I'm pretty sure that's basically noise, because it looks 1 over Fe, so yeah. Okay, I'm off. Bye, guys.